Welcome back. So we were talking about basically decentralized deep learning paradigms, and we wanted to see how we can solve these training problems in a decentralized way. We talked about a simple problem first, the consensus problem, where each agent is holding some number locally, and we talked about the consensus algorithm. Okay. But that's not basically adequate, again, because we have training problems in general. So we want to see how we can leverage this simple average consensus algorithm and integrate it with the training algorithm, such as SGD, ADAM, and other methods we've talked about in the class so far. Okay. So let's recall our problem then. Our problem is to minimize the average loss. The average loss of the agents. Okay, so we want to find this W star, where each local loss itself is, let's say, some stochastic function, such as the average loss over the training data that is held locally by agent J. Okay, now in the simple case where these fj's were quadratic, we talk about the consensus algorithm, where in the matrix form it takes this very neat expression, which again we can think of it as the fixed point iteration, okay, or an instance of the fixed point iteration algorithm. But in terms of what is happening locally at the agents, what we are doing is that we are receiving the messages from our immediate neighbors, and then we are performing a weighted aggregation, or we are performing basically a weighted average. Okay. All right, so now we want to build upon this and solve this more general problem. So let's think of this update in a slightly different way. So basically what is happening is that everyone is sharing their current model updates with their neighbors, and then everyone is performing local aggregation. Okay, so I receive one model updates, another model updates, and then my own model update, take the weighted average, and then we move on to the next iteration. All right. So therefore, if we are communicating model updates, maybe in the for the optimization case, for the training problem, we should also share with our immediate neighbors our local model updates. So it seems something intuitive and reasonable. So why not try that? And in fact, this is what we're going to do. Okay. So we're going to follow a similar pattern, and we're going to share local updates. What's the simple local updates we've talked about in the class numerous times? That is basically when you update the current solution to the next one by going along the negative direction of the gradient or stochastic gradient times some learning rate. Okay, so this is what we're going to communicate. Okay, everyone is communicating that. And then we are basically performing a weighted aggregation like before. Okay, and this will be our next update that we're going to use again later on to basically update it according to our local data to refine our solution. Okay, so note that this stochastic gradient GTI is basically the stochastic gradient or the local stochastic gradient of agent I at time t. So essentially, the agent I is generating a mini-batch at time t, and then is calculating the mini-batch gradient, and is using that to update its local parameter, and then it will share the result with its neighbors. In matrix form, this is also going to result in a very neat expression. So what we are doing is that, again, we're going to go from the current solution to the next one by following the direction of the gradient times some, following the direction of the negative gradient times some learning rate. Okay. But again, because it's a decentralized problem, we are performing local aggregation. So we multiply with this matrix W. Okay. So this matrix GT is basically a matrix that collects these local stochastic gradients as its columns. So the first column is the local stochastic gradient of agent 1, second column local stochastic gradient of agent 2, etc. All right, so this is our simple algorithm. And one question is that, therefore, can we maybe come up with better algorithms? And the answer is yes, right? So here we are integrating the simple SGD algorithm. We can use more advanced training algorithms, such as those we've talked about in the class, like Adam, maybe SGD with momentum, or debias SGD with momentum, etc. So we talk about all of these key components, such as adaptivity, pair coordinate rates, and momentum variance reductions. All of those can be integrated in the decentralized case as well. Okay. So therefore, we can use more sophisticated, more advanced local update strategies. Similarly, we can actually use more advanced or develop more advanced aggregation mechanisms. One way to see how we can do this is to, again, go back to the connection to fixed point. Okay, so we saw that this is basically an instance of the fixed point iteration. We also talked early on in the class about the connection between gradient descent and fixed point iteration. So we were able to improve gradient descent and the stochastic gradient descent by developing these key components such as adaptivity, momentum, variance reduction. So those can also be integrated in some sense to develop more advanced aggregation mechanisms, more advanced consensus mechanisms. And indeed, there are lots of elegant ideas in the literature building upon these components I mentioned to improve not only the local update step, but also the local aggregation step. Okay, but nonetheless, again, everything builds upon this decentralized SGD algorithm that we just talked about. Okay, so another question is, what's the performance of this algorithm in terms of the convergence to a solution? Okay, it turns out we can prove this simple theorem. So let's assume that the graph is connected and our weight matrix is doubly stochastic. Again, that means that the weight matrix is symmetric. Sums and rows sum to 1, columns also sum to 1. Okay, and we also have a spectral gap which is going to be between 0 and 1. Okay, so again, rho is something that is between 0 and 1. Okay, and if I assume that the graph is fully connected, the rho will be exactly 1. And if I assume the graph is connected, so it's not disconnected, rho will be strictly away from 0. Okay. Now let's define the consensus error like we did before. Okay, so it's just the average deviation of local parameters from the current average value. Okay. So the only difference between this and the consensus error we talked about in the simple case before, simple case of consensus before, is that now this matrix or this vector are time varying. Okay. All right. So this is the assumptions on our communication graph. So we also need some assumption on our function that we are minimizing. So let's assume that the loss function, the global loss function, is L smooth. Furthermore, assume that each agent has access to a stochastic first order Olacher, which basically means that they can generate unbiased estimators of their true local gradient with bounded variance. And let's also assume that the local minimatches are statistically independent. So this is exactly the same assumption we had for when we analyze SGD and its advanced versions, such as SGD with momentum. All right, so under these assumptions, if we set the learning rate to be crucially proportional to rho and inversely proportional to a square root of t, we'll be able to establish this result. Okay, so we're going to bound two terms simultaneously. One term is basically talking about the sort of the optimality of the average iterate xt. The other term is talking about the consensus error. Both of these terms are easy to see that they are non-negative. So we are bonding sum of two non-negative terms, so which means that each term individually will also be bonded. Okay. What is our bond? What is the essentially what is our convergence rate? Is going to be something that depends on 1 over n squared of t, and it's also related to 1 over rho. Okay, so it could be a polynomial function of 1 over rho, something like 1 over rho squared. Okay, right. So therefore, under these conditions, we are going to bond both the consensus error or the average consensus error, as well as our notion of first order optimality at the average iterates, okay, or at the average model. Okay, so this result is therefore saying that the average iterate is going to be a first order solution, but that is not adequate because the average iterate is not a known quantity to the agents. So if we are all holding different quantities, but the average is basically, let's say, the optimal solution, that doesn't necessarily mean that our local solutions are also optimal. Okay, so therefore this is not enough, but fortunately we are also bonding another term at the same time, and that is related to consensus. So the second term being bonded is saying that the consensus error is vanishing, okay, with the rate of 1 over the square root of t. So that means that everyone is converging to the average value. So collectively, this theorem is saying that the average value is converging to a good solution, everyone is converging to the average value, so therefore everyone is converging to a good solution, and we're going to reach consensus. Okay. Now let's also talk briefly about the role of rho, the spectral gap. Remember again that rho is some notion of connectivity. If rho is large, near 1, graph is well connected, so we should expect a faster convergence. And that is indeed true, given that the convergence is, depends on the reciprocal of rho. On the other hand, when rho is small, near 0, the graph is not well connected. So we expect that it takes more time for the messages to be propagated over the network, so therefore the convergence has to be slower. And again, this is something that is reflected in our bond. Finally, let's also talk about the regulating role of the learning rate, eta. Eta depends, is proportional to rho, which basically is saying that if the graph is well connected, I am allowed to use a larger learning rate. On the other hand, if the graph is not well connected, rho is small, I have to adjust my learning rate such that I use a smaller one to make sure I still converge, or the algorithm still converges. Okay, so is rho, and one question that could arise here is that whether rho is a quantity that is known to the agents locally. And in many cases, rho in fact is a global property of the communication graph. So the agents may not necessarily be able to know what rho is. So one question therefore is that, can the agents estimate rho on the fly, maybe using some version of the adaptive algorithms we talked about? That is a good question, I would say, and there are some interesting results in the literature trying to answer questions of this kind. Okay, so this is therefore our theorem. So let's very briefly talk about the main steps to prove this theorem. It is going to follow the template we've seen a couple of times so far, the potential-based analysis. Okay, so in particular, we have this important source of error that is impacting our convergence. That is the consensus error. In the context of SGD with momentum and deep-bias SGD momentum, where we saw this potential-based analysis, the important source of error that impacted the convergence was the estimation error, or the gradient estimation error. Okay, so we have the source of error, therefore, so it is natural to talk about this potential-based analysis. There is actually one difference, and that is that instead of studying, let's say, the performance of these k local models, things that we know, we're going to study the performance of the average model, x bar t, which is a virtual sequence unknown to the agents. So that is just one change with, compared to our previous examples of this potential-based analysis. Okay, and this is actually also in some sense a generalizable pattern, because sometimes when you want to study the performance of training algorithms, you may need to again see how a visual sequence, something that is not necessarily known when you run the algorithm, is going to evolve. And in fact, we're going to talk about another examples of this in our next lecture on communication compression mechanisms for distributed deep learning. Okay, so with that, therefore, it's going to be essential to study how the consensus error evolves over time. Using our assumption, we'll be able to establish this recursive inequality that says that the consensus error at time t plus 1 is bounded by rho times the expected consensus error at time t plus some other terms. Okay. But what matters is that this is in our nice form that we've also seen before. So this immediately reminds of this potential-based analysis. We're going to define a potential function which has two parts. One part is about the suboptimality of the average iterates. Okay. And the other part is basically about this additional source of error impacting our convergence. We're going to therefore study the evolution of this potential function by solving over its consecutive differences and then using the assumptions such as L smoothness of the function. And fortunately, given that we have this very nice recursive inequality and rho is strictly less than 1, we can find a good constant to ensure convergence. So I just realized I have a typo here, so it should be 1 minus rho actually, not rho. Okay, so 1 minus rho is strictly less than 1, which basically comes from the fact that rho is strictly larger than 0 and the graph is fully connected. Okay, so with that change, then therefore what matters is that we have this nice property such that the error basically at one time is the error at the previous time times a constant which is strictly less than 1, and that will enable us to find this good constant CE and ensure the convergence of our decentralized SGD algorithm. So as I mentioned, we're going to basically see another convergence results that follows this template, but in the context of communication compression mechanisms for distributed deep learning, which is the subject of our next lecture. I'll see you there.